begin my presentation. And okay, thanks to the host, and welcome to our presentation. I'm Weizhen from Shanghai Pugo Mountain Company. And today I will show our MBSA practice in COMAC with Wan Rang, and who is an excellent system engineer of COMAC in our project. The theme we share today is the practice in COMAC to conduct MBSA in Avionics Systems based on Capella. The whole practice was jointly completed by COMAC and PGM. And our presentation today will also be divided into two parts. In the first part, I will give a brief introduction to the background of the whole practice. And in the second part, Wan Rang will tell you about our practice in detail. And first, I will give a brief introduction to PGM and COMAC. Our presentation was completed in SADRI, and it's an abbreviation of Shanghai Aircraft Design and Research Institute, which is the design and research center of COMAC. COMAC functions as the main vehicle in implementing large passenger aircraft programs in China. And the SADRI is responsible for the engineering design tasks and the overall technical grasp of China's civil aircraft projects. PGM is a short for Pugo Mountain, and which comes from China's earliest geography, Shanhaijing. And the PGM is a leading provider of MBSE solutions and consulting services in China, and has many important partners in aeronautics and astronautics domain. And PGM can provide many add-ons for Capella, including functional simulation, parameter management, collaborative modeling, safety analysis, etc. Next, I will briefly introduce the background of our practice. First, let's have an overview of avionics system. It includes display and alarm system, navigation system, integrated surveillance system, flight management system, and avionics core processing system, etc. And as we know, safety analysis is an important part in aircraft design. The safety analysis of avionics system is one of the most challenging parts because it involves highly integrated avionics public resources, in which a large number of core parameters are transmitted. Traditional avionics system safety analysis is document-based, involve different contextual toolchains. The traditional avionics system safety analysis is document-based and involves different contextual toolchains, which has the following four problems. The first one is the process of safety analysis is isolated from the safety architecture model, of the system architecture model. The establishment of fault tree relies on the abstraction of system architecture, which really depends on the designer's personal experience. And meanwhile, it's difficult to verify safety requirements of system architecture. The second problem is the process of fault tree creation lacks standardization. The avionics public resources are referenced by different subsystems. And the same avionics public resources have different naming rules in different fault trees, which make it difficult to assess the impact of avionics public resources failure for different subsystems. The third problem is the fault tree cannot be created automatically. The traditional fault tree is created by the designer manually, which relies heavily on the designer's personal experience, and the result is subjective. At the same time, with the increasing complexity of avionics system, the creation and maintenance of fault tree is very laborious and error-prone. The fourth problem is the safety impact analysis cannot be performed automatically. The result of fault-free minimal cut site need to manually create a safety database, which will be used for safety impact analysis. And meanwhile, the fault-free of different systems cannot be integrated automatically at the aircraft level, and the systematic cascading is time-consuming. Faced with the problems above, COMAC and PGM began to explore and practice MBSA in avionics system. In the traditional ways, FHA, PSSA, and other processes is performed through traditional documentation, and different tools are involved, including Microsoft Word, Excel, and different fault-free analysis tools. In 2018, COMAC began to introduce the technical route of Capella for MBSE modeling. From 2018 to 2022, the whole process for Capella SA to PA was completed. At the same time, the aircraft level model integration based on Team for Capella was realized through extended development. Based on the practice of the above two processes, in 2023, COMAC and PGM put forward the Avionics MBSA method, which coincided with 4761. At the same time, the MBSA modeling client COMSPEC was published. And now let me introduce our technical path briefly. First of all, the system engineer needed to complete the physical model of Capella, and the safety engineer can conduct FHA analysis based on the physical architecture model and define the failure conditions. The PSSA can be conducted based on the physical architecture, and the failure mode and the failure propagation model can be established, as well as the occurrence conditions between FC and FM. After that, COMSPEC can automatically create the fault tree according to FC occurrence conditions and the failure propagation model. Finally, the fault tree is calculated, and the result of minimal cut size will be saved to the safety database with one click. Based on this database, designers can choose any failure sources to analyze its safety impact at a system level or aircraft level. And all these steps can be done in COMSPEC. And next, Wan Rang will introduce COMSPEC in detail.
Hello everyone, I'm Wan Rang from COMAC. I will introduce the specific content of the COMSPEC platform below. The COMSPEC platform is a model-based safety analysis platform dependently developed based on the MBSA concept and combined with the MBSE physical architecture and the safety analysis characteristics of the Avionic Systems. That means the requirements of SAE-ARP 4761. It mainly includes 6 major functions. The first one is to complete the physical architecture model in Capella. This part of the MBSE modeling work, including the configuration of network resources and the automatic modeling, which was shared on Capella Day last year. The second one is failure modes and failure conditions management. It can support to import the existing failure modes and failure conditions and establish a database. The third one is failure propagation modeling. It can support to generate fault tree automatically. COMSPEC can support importing fault trees from different tools, including RAM Commander, Modini, and Graph. The last one is safety analysis. It can import the specific risk combinations and supports BRA, ZXA, ZSA exact. It can also export FTA reports and FMEA reports. The platform supports a collaborative modeling environment. The following is the technical process of our entire platform development. First, we built functional and physical architecture models based on Capella, including building functional models of each system hierarchically, implementing functional and logical redundant designs, and finally building a complete physical architecture model. The second step is to analyze the functional architecture, define the internal failure modes and interface failure modes of the functional and architecture, and define the failure propagation path and the logical relationship of each module. Finally, definite the failure conditions and associate with the functional interface failure modes to complete the failure propagation modeling. The third step is fault tree analysis, which automatically creates a fault tree through the failure propagation model, conducts qualitative and quantitative analysis of the fault tree, and build a safety analysis database of the range of the whole airplane. Based on the database, single-point failures, combined failures, cascading effects, and common cause can be analyzed. The analysis results can confirm the physical architecture and safety requirements. First, we will introduce the functional and physical architecture model. The idea of system engineering of COMAC is from needs to functions to requirements and finally to the products. Based on this idea, modeling is done at the aircraft level based on Capella software and combined with aircraft level scenarios. Aircraft level functions are defined and OASA are established. Then, at the LA level, aircraft level functionalities is assigned to the systems. In the system model, functions are further refined and improved according to the system level scenarios to get the SA. Then, the LA layer implements the redundancy of functions and interactions, and finally implementing both functions and logical into component level, and at last get a system-level physical architecture model. After the system-level model is established, LA and PA can be integrated into the integrated model to configure network resources. The integrated model assigns the configuration results to the system model, and then completes the whole functional and physical architecture model from aircraft to system level. During the modeling process, each system can work together in real time across projects with modeling functional and physical architecture levels. Interfaces can be synchronized to interactive systems in real time, making the modeling environment more convenient and efficient. The following is functions and architecture analysis. The first is failure modes management. Based on the previous functional and physical architecture models, a failure propagation view of each module can be created. Then, internal FMs can be created for the components, which represents the internal failure of the physical component itself. Interface FMs can also be created for components and functions to represent the interface failure. Failure modes created on the failure propagation view can automatically added to the FM libraries. The platform also can import the existing FMEA data. It can be in Excel and XML formats. The import FMEA data will also be stored in the FM libraries. Imported FM data can be automatically associated with model elements based on key information such as component numbers. The following is to build a failure propagation model. Based on the Capella modeling methodology, functions are allocated to logical and logical are allocated to the components. The failure modes established at the component layer will be automatically and synchronously transmitted to the logical layer. and the failure modes of the logical layer will also be synchronously transmitted to the functional layer. Functional transmission of components to logical to function is realized. Failure propagation between components will also be automatically synchronized to the corresponding components interface based on the actual physical connection between components, as will failure propagation between functional interfaces. After establishing the internal fault modes and the interface fault modes of the components, the failure propagation path and the failure propagation relationship between these fault modes are graphically defined. Failure modes at the interface can be automatically passed and synchronized based on the connection relationship. The failure propagation model of the functional layer is the same as the physical components layer. The failure modes of subfunction will transmit the failure to its parent function. Then we can establish the parent functional propagation models. After establishing the failure propagation model, we can define the conditions for the occurrence of FC. Associate the failure condition with the output interface failure modes in the functional failure propagation model. When FC involves multiple subfunctions, it can also be associated with FM in the parent function failure propagation diagram. All defined FCs will also be stored in the FC library. When FC involves different aircraft functions, a failure condition definition diagram can be drawn to establish a failure logical propagation relationship between the failure conditions and the multiple aircraft function FMs. In this way, multiple subtrees can also be created into a complete fault tree. After defining FC, a fault tree can be automatically established based on the failure propagation model. Events where are automatically generated in the fault tree based on the physical connection bus type between the actual components. The probability of occurrence of the basic event is the failure rate of the corresponding function FM or components FM in the model. After the fault tree is generated, quantitative and quantitative calculation can be performed so as to support minimum cut set calculation. The platform can automatically calculate the probability of the top event based on the failure rate of the basic event. Based on the previous failure propagation model, the platform can form a safety analysis database of the range of the whole aircraft. Based on this database, the platform can support safety analysis of single points failures and combined failures in different functional scopes. For example, if the single point of the left component is failed, the left redundant function will be failed. When the combination of the left component and the right component fails, it will lead to the loss of the entire function B. We can make the safety analysis in different function scopes. It can be one or several fault trees, one or several functions, one or several systems, and even the whole aircraft range. The platform can also define a CCA library. From the CCA library, the defined common cause sources can be associated with FM to support common cause analysis. Component FM can be managed according to attributes such as zone, component safety level, system, and subsystem. And by filtering these attributes, it can support PRZSA. For example, if the failure area is screened to the left, we can get the FM1 and FM3 failures. And then a combined failure is performed on the two failure modes. Based on the safety analysis database, the impact analysis of the combined failure is performed so that PRA-ZRC can be analyzed. This is the software interface of our safety analysis. We can choose the type of the failure to analyze, including failure modes, logical gates, CCA. After choosing the analysis type, we can select the corresponding analysis object from the model database. Finally, we can select the scope to be analyzed, which can be a certain ATA, function, fault tree, or several. In conclusion, the platform can analyze the complex system architecture based on the whole aircraft safety database. First one, this platform can support single-point failure analysis, and the second one, it can make combined failure analysis, especially the impact analysis of public resources like ACPI system or power supply in different functional scopes. The third one, the platform can support common cause cascading analysis, such as PRA, ZRC, and CMA. And the last one, it can support generation standard reports compliant with ARP 14761, database management, exports FTA, FHA, FMEA reports. The avionic system of some type has been analyzed using this platform. This is an example of analysis of the failure of two switch combinations. The left side is the result of manual analysis, and the right side is the result of platform analysis. It can be seen that the accuracy of the platform analysis result is consistent, and the platform analysis is more efficient, objective, and complete. And next is a little video demo of the platform. This is an example of a simple display system with dual redundancy. Both the data source and the display function have two redundancies, and they are cross-connected. A parent function failure propagation diagram can be established to show the failure propagation relationship between two display subfunctions and parent functions. Among them, FM will eventually lead to the occurrence of FC, and the occurrence conditions between FC and FM can be established in the property page of both FC and FM. Within each leaf function, the failure propagation can be defined among function inputs, software, hardware, and function outputs. Other function failure propagation are similar. In the same way, we can define the failure propagation relationship for logical and physical components. Based on the defined FC and the failure propagation model, we can automatically generate the fault tree for each FC. The top event of the fault tree is consistent with the logical defined in parent functional failure propagation diagram. And the middle layer of the fault tree is consistent with the failure propagation logical defined in leaf function logical components. And this is the middle gate. The basic event is the failure of two data source components, display components, and EVAs. And this is the component device. After the fault tree is generated, quantitative and quantitative calculation can be performed. We can get the minimum cut set of every logical gates. And then we can save the result to the database. Then, based on the database, we can do the safety analysis. First, we can choose the analysis type, including the components FM, functional, FM, CC, and the middle gates, and then choose the analysis object from the model database. At last, we can choose the analysis scope, several ETA, several functions, and several fault trees. And there we choose one fault tree. And this is the result. And the result can also be highlighted in the fault tree so that you can see more clearly how the results were cast. Okay, the demo is over. And this is the last section. It's a summary. This platform has the following advantages. The first one is that the safety model and the physical architecture model can be traced, and the safety analysis result can confirm and improve the architecture models. The second one is the naming way of the public components is more standardized and consistent, making it easier to conduct safety analysis of the range of the whole airplane. The third one is according to the failure propagation model, the failure tree is automatically constructed and saving people's time and efforts. The fourth one is safety analysis is automated based on the database, which also is automatically formed. Complex system analysis can be performed based on the database. It is more efficient. For the last one, for other innovations, this platform is compatible with fault tree or for other FTA tools, and the platform has intellectual property rights. The COMSPEC has a wide application. Now, it has been used in the C929 aircraft avionic systems. Furthermore, it can apply to the design and verification of complex systems design like aviation systems, airspace, nuclear energy, vehicles, ships, and so on. This platform also can be applied to industry fields, which requires the driving force of the high system integration and high requirements for reliability and safety. Okay, that's all. Thank you for listening. And it's the time for Q&A.
Okay, many thanks both of you for this really clear and detailed presentation. Before we go through the presentation, let me just introduce you with Renfei Xu, which is also a member of PGM, and who will ensure well, the translation in case we need it. So let's jump to the first question we have. What benefits does COMSPEC offer compared to a program like Isograph for reliability workbench? Is this one considered superior to the other?
Okay. Okay, so I will answer this question. You know, in Isograph, we cannot combine the system architect model with the safety analysis model, so we need to create the fault tree manually. And in COMSPEC, we can build our safety analysis model directly based on the architectural model, the Capella architectural model. So that's why we prefer COMSPEC over the Isograph reliability workbench. So the problem is the same with RAM Commander and something some other tools like them. So yeah, that's the answer.
Okay, thanks for that. Next one. Did you use Capella standard features or the fault or failure mode analysis, or did you have to create this yourself?
We have developed an extra module based on Capella. We call it COMSPEC. So the failure model, the fault tree, and all the models related to safety domain is created by our extra add-on.
Can Capella, based on built model and determined manual cut set, automatically generated the requirement for FDAL and IDAL?
I think the maybe FDAL and IDAL should not be generated by the minimum cut set. I'm not sure if I have understand the question correctly.
Okay,
so
maybe
yeah.
You can ask Anastasia to provide details, and we'll try to provide a more accurate answer later. Let's jump to the next one. Or are external events or events related to specific flight phases managed? How do you identify the presence of failure mode? And are they applicable in a given area to perform ZSA or PRA?
So we have considered the flight phase, and we can manage the flight phase informations in the failure condition, but maybe there is not much consideration for the external events. They can be described in the failure condition.
Next one, and we still we still have time for maybe one or two questions. So feel free if you have one. Does Capella support multi-languages? In your case, are you using English or Chinese in your model?
Yes, in our model we can use Chinese characters to name our function or components, and we have also done some localization in China, so the Capella application can be shown in Chinese, but in most cases we are using English in the modeling, I think.
Okay, next one. Thanks for this clarification. Can COMSPEC run ISO 262?
I think it's not. The COMSPEC is produced based on the civil aircraft domain, so we have not considered the automotive industry. So yeah, it's mainly based on 4761.
Okay. Thanks for that. Well, we have 15 minutes earlier. So, well, we definitely have time if the attendees have a few additional questions. And instead, maybe you had some. Well.
Oh.
Okay, so we received this question in the meantime.
Okay.
What is the learning curve for this add-on?
I think it's not difficult to learn. So for the users who are familiar with isograph and reliability workbench, I think they can easily use COMSPEC.
So the presentation. How many system layers were in scope for cascade analysis?
Our cascading analysis is based on the physical architecture model, and our cascading analysis is based on the physical architecture of the aircraft, and it is carried out based on over 30 ATA systems, and the upper level is the aircraft itself. So I think it's maybe 2 layers, the aircraft and the ATA system.
Okay, thanks for that. Yeah, well, this one is also interesting to have in mind. Is COMSPEC free? Is it possible to download it?
No, it's not free, and if you want to try it, you can contact PGM
And are there any new features or improvements you're planning for this add-on?
Okay, so I think the question is for COMSPEC, not for Capella, right?
Yeah, probably.
Yeah. Okay, and I think at least one improvement we are trying to do is by now the safety analysis is totally based on physical architecture, and maybe in the future we can support the safety analysis based on logical architecture, the system analysis. So yeah, maybe that's the future work.
Okay, and you probably provide a partial answer to this question, but maybe it's an opportunity to provide details on which kind of application COMSPEC have been used. Has COMSPEC been used to support certification?
Which kind of application? So Wan Rang have mentioned that COMSPEC has already been used in the design of C929 in COMAC, and for this aircraft is still not in the certification process. So the answer for the second question is not yet.
Okay, but you're planning to.
Yeah, we are planning.
Okay, and this one also I had already a partial answer, but can the tool help to produce functional or design failure modes and FMEA?
Yes, FMEA, FMECA is the basic feature of COMSPEC, so we can produce the report automatically.
Thanks again for your presentation, for your time, and for sharing with us.
Okay, bye.
Bye.
Bye.